Hello, Daniel.
Hello, John.
How are you today? Great to
I
see
am
you.
thank you very well. I'm very well, thank you.
Welcome, Daniel Shapiro from SES O3b to a discussion with Tekedia Institute.
My pleasure.
We're going to kick off with something quite easy. It's a trip down memory lane, really, because you've been in the industry now since when, 2007, earlier, maybe?
I've been in the industry, yes, since 2007. Yeah,
And
indeed.
you were with Gillat, and then you were with O3b since the startup, and
Exactly.
then you sort of uh, went along with the takeover with SES, so you know everything from the ground up, right from the very start of the
Yes.
and you've probably seen a lot change, not only in the industry as a whole, but also specifically for our African audience. And maybe you can, shed some light and some ideas on that.
Yeah. Well, I think that the African market in regard to satellite has seen two major disruptions over the last 10, 12 years. The first big disruption was the appearance of fiber.
Mm-hmm.
Fiber that came in first, I think it was in the East Coast in Kenya, with the appearance of the Easy and the Teams cables. And then on the West Coast came the wax and all the other fibers that you have today. There's a plethora of submarine cables connecting Africa to the continent, to Europe and other continents, and I think that had a very profound positive effect on the way that Africa connects to the world. In regard to the satellite market, one of the things that it did, it decreased the cost of satellite that was very expensive. And it definitely improved the quality of connectivity, at least the international quality of connectivity that the Africa continent had, mainly because there's a big difference between geostationary satellites and fiber, and that is the latency.
Mm-hmm.
There's also a difference in the cost structure of fiber and satellite. In satellite, you don't spend a lot to deploy the satellite relatively, but then to operate it is very expensive. On the opposite, to deploy a fiber is tremendously expensive, but then to operate it is cheaper. In regard to the end user, this is an advantage.
Mm-hmm.
The second biggest disruption that the African market had was the launch of O3b. That was the first low latency system based on satellite that Africa ever had. And well, it allowed people to benefit from the benefits of fiber in those places where fiber was not present.
Mm-hmm.
So I think that summarizes more or less everything.
So you've mentioned an interesting aspect that you distinguished between some of the types of satellites that were around before O3b came along, and you specifically mentioned the latency. Now I understand that there is roughly three different types of satellites, which is mostly about the distance they are from the Earth. You've got the traditional style high orbit satellites, and then you have the middle Earth orbit satellites like O3b, and then you've also got the low Earth orbit ones. Can you tell us a little bit about those?
Yes, of course. So the traditional satellites are the geostationary satellites. Those satellites are satellites that are positioned at an orbit which relatively to Earth is fixed. because the satellites on the Earth will rotate at the same relative speed. Those are positioned at 36,000 kilometers above the Earth. And one of the main aspects that these satellites have in regard to the latency is the high figure that you have over there, and that is given by the distance. So roughly a typical geostationary satellite will give you a latency of about 600 milliseconds, which is kind of not good for nowadays data applications. On the other hand, one of the benefits of the geostationary satellite is that it's going to cover huge masses of territory when covering that territory with a footprint. Usually, a geostationary satellite will have the coverage of a whole continent or even a whole hemisphere. And there have been some changes in the traditional geostationary satellites. Now you have satellites that are called HTS, high throughput satellites, which are going to provide you a lot of bandwidth. Most of the previous geostationary satellites would operate in C-band and in Ku, with transponders the size of 36 megahertz, of 72 megahertz of size, and with the spectrum efficiency that you could get like, I don't know, 100, 200 megabits per transponder, which was a lot, but today is not significant. The HTS high throughput satellites of today, they can provide much more capacity than that, but still with a very high latency.
And is that HTS also making it cheaper for customers in the end, or has it impacted on that? Or
well, sometimes yes, because in essence, the price that a satellite operator is going to put on the bandwidth is based on how long it's going to take him to get a return on investment on the huge investment of launching a satellite, right? The more capacity that you have, then the cheaper you can sell is that capacity and still reach your ROI according to your business plan. So yes, it does have an impact on the users, but still, geostationary satellites are good for broadcasting, for example. But for data applications of today's, they lack the speed that those applications require, such as cloud computing.
Okay.
The second category of satellite, or actually let's talk about the third category of satellite, and those are the LEO satellites. So LEO are low Earth orbit satellites. Those are positioned, at orbits that range between the, I don't know, 150, 200 kilometers up to 1,500 kilometers. It's a very wide range. And in the last few years, we have seen more and more new satellites being launched. For example, you have Elon Musk Constellation Starlinks, and then you have OneWeb, and there are others in the make. One of the advantages, a couple of advantages that these LEO satellites have is, first of all, the latency that they will provide. They're going to provide a very low latency, about 25 to 50 milliseconds, which is like a tenth or less than what a geostationary would provide. And the cost of the satellite is very low. But on the other hand, a LEO constellation, in order to provide coverage to a specific portion of the Earth, they're going to need a huge amount of satellites, hundreds, if not thousands, of satellites per constellation. And although this constellation started to work already, nobody actually is going to know how they're going to work going forward. Once, I don't know, they reach the 1,000, 2,000, 3,000 satellites that they will need in order to provide a coverage to the whole Earth. Now, the problem is that these LEO satellites, they are smaller, they are cheaper, but also their lifespan is also shorter. If a geostationary satellite is, has a lifespan of 15 years, a LEO satellite will have a lifespan of 5 years. Now, if you take into consideration the fact that they have such a short lifespan and you need so many satellites, one of the things is that these LEO companies will constantly need to manufacture and launch satellites.
So it's going to be a really high operating cost then for a LEO
It's a very high maintenance system.
Yeah.
And actually, until now, nobody knows if those business plans are going to hold water. Nobody knows. Right now, also, all the LEO systems that we are hearing about, they are approaching a very specific segment of the market, which is, the SOHO market, the small home, the small office, home office users. So, for example, Starlink is offering to its users 150 megabits per second at a very low price. But then the contention rate that they're applying on those satellites is very, very high. Now, the first users are not going to notice anything. But when the system starts gaining users, and those, in order for this to be viable commercially, there will be millions of users, then they are going to feel, the problems that working in a high contention system brings with.
Can you elaborate a little bit on contention? Because maybe some of our viewers may not know about it.
Of course. So when you buy, for example, let's say that well, this is not very popular in Africa, but let's say that you get an internet connection, right? And let's say that you go and you buy from a provider an internet connection of 100 megabits, which can be on Wi-Fi. That's for Africa. It can be on DSL. It can be on anything, right? The thing is that you buy 100 megabits. But the thing is that the provider is never going to give you 100 megabits of dedicated capacity, which is fully dedicated with you. You are probably going to share that capacity with many other users. For example, a typical internet provider will give you a capacity, a contention rate of 100. That means that 100 users are going to share those 100 megabits. It's a statistical thing. Like, they take into account that not everybody is going to be using those 100 megabits at the same time, and not the 100 users are going to generate 100 packets at the same time. So more or less it works. But it works only for those customers, that are home users or small users, not for intensive users, let's say like a very big business, like a bank, like an internet provider, for example. If you have an internet provider that is going to buy a satellite with a contention rate of 100 and is going to apply on that also his contention rate of 100 to make more money, that's called overselling. Then actually the contention rate that the user is going to have is 1 to 10,000. So that's no good. So the LEO satellites are good for specific tasks. The geostationary satellites are good for other type of tasks. And then you have the MEO satellites. Now, the MEO satellites are those satellites that are positioned in a mid-Earth orbit, mid-Earth orbit. That's a height of about 8,000 kilometers above the Earth. Currently, the only constellation is the O3b constellation, which has been operative since 2014. The satellites that O3b has currently, SES, we have 20 satellites in orbit. Each satellite is able to yield 10 beams. Each beam has a maximum capacity of 1 gigabit. That's a lot of capacity. There's no geostationary satellite that can do that. The advantage also that these satellites have a relatively low latency of 150 milliseconds. although LEO has a lower latency, the difference between 50 and 150 for our purposes, it's almost the same. Like nobody is going to note the difference between 50 and 150. And that has something to do with the way that, you know, in IP, the handshake process works. For example, when you have 600 milliseconds, then you send a packet and then you get a packet back. And that server that sent you the packet back is waiting for the handshake in a certain amount of time. And when it's not getting, then it's decreasing the priority by which your packet is going to be treated. And therefore, you know, a whole thing happens. And in certain applications, you're going to time out. You wouldn't be able to stream the data the right way. So it's very problematic. Now, 150 milliseconds is the sweet spot of that. And you can do everything that you can do with a 50 milliseconds in what we think is a more efficient way in regard of maintaining a system that is not that high maintenance as a LEO. And thus, you know, we started in 2014 with our system that today has 20 satellites. And we are launching our next generation satellites, which is called Empower, which is also going to be located in a mid-Earth orbit. And the Empower is going to have some additional benefits compared with the classical 3B that we have.
Thank you so much for that one, Daniel.
Yes.
So some customers are getting services directly from satellite providers, and some customers are getting services indirectly where you've got satellites in the mix, but they're actually getting it from a retailer. So do you have any ideas about the types of services that can be got directly from satellite providers, or the ones that are available from retailers where they're using different architecture and different services in the mix?
Well, mostly, you know, satellite providers are usually large companies, and they will tend to work with very large customers. So mostly a home user cannot go to a specific provider and tell them, well, sell me a VSAT, right? And VSAT is the smallest form of satellite connectivity that a user might have. But it doesn't matter then. You can go to a reseller and tell them, listen, Mr. Reseller, I would like to have in my remote location a VSAT, which is composed of a small antenna, which is composed of a modem and some other stuff. And I would like to get a connection of, I don't know, 1 megabit, 2 megabit, 3 megabits, whatever. And then you would get that connectivity. Pricing, you know, differs depending the frequency band that you will use. Is it going to be C-band? Is it going to be Ku band? Is it going to be Ka band? It also depends on the contention that you're going to have. Are you going to have dedicated capacity because you're a significantly large business, or are you going to have I don't know, small capacity with high contention? There are many options, and the pricing is going to range, you know, through a very wide spectrum. Now, all these satellites, all the VSAT satellites are geostationary. The exception to the rules are going to be the Starlink satellites, which are not going to be a GEO, but are going to be LEO. So in summary, a user can get a direct connectivity to a satellite through a VSAT, or they can get indirect connectivity, and many users in Africa today actually have that, you know, through a provider that buys its internet connectivity through a satellite and then gives it to its users. For example, in DRC, we work with all the mobile network operators, all of them, and we provide to them huge amounts of satellite-based internet with low latency. And that same capacity that they get, they distribute to their customers through LTE or 3G or whatever.
Now, Daniel, thank you for that. You touched on something very important there, which you mentioned different types of bands. Could you mention or explain a little bit about that
Yes.
for us?
Yes, absolutely. So there are three types. There are many frequency bands, many. But in regard to communications, let's concentrate on the three main ones: C-band, Ku band, and Ka band. I'm not going to mention the numbers, but C-band are lower frequencies, K-band are higher frequencies, and Ka are the highest frequencies of all. Two main differences. The lower the frequency, the less capacity that you have available. So a C-band will have less megabits than a Ku, and a Ku will have less megabits than a Ka. So that would be the advantage of Ka. On the other hand, the lower frequencies are better suited for heavy rain zones. And mostly sub-Saharan Africa is a heavy rain zone. So when it rains, every wireless connection is going to be affected, be it a Wi-Fi or whatever. Wireless is affected by rain.
That's rain fade, right?
Yes. Now, the rain fade, yes. C-band is going to be less affected. Ku is going to be a little bit more affected, and Ka is going to be even more affected than Ku. So that's a thing that customers need to take into consideration. There are ways to overcome, the rain fade effects. For example, we operate in Ka, but on the other hand, for our customers, we deploy what we call diversity sites. What's a diversity site? Instead of having one antenna, we have two antennas separated by each other by a distance of 10 kilometers. And statistically, we know that the size of a rain cell is not more than 10 kilometers. So if we put one antenna here and one antenna here, apart 10, 15, 20, whatever, kilometers apart, statistically, it's probable that if this antenna is down, this one will be working, and vice versa. And therefore, that way, we can provide continuity in the service. That's what we call resilience. But those are, again, solutions that are for the larger customers, for the cellular operators, for the large ISPs, those type of customers.
Thanks for that, Daniel. Now, one of the things you mentioned earlier, which was, the difference between different solutions, and that some of them, the CapEx can be high, some of them, the OpEx can be particularly high. But of course, some companies, they do things through joint ventures, or they contract out a lot of the work, like they get other people to put their satellites in the air. They get somebody to manufacture it. Do you have any view on whether companies should do everything themselves end to end, or do you think it makes more sense to diversify and have different companies?
Well, it depends. It depends who you ask, right? If you ask Elon Musk, he does everything. He does his satellites, he does his antennas, he does the launching, he does everything. Also, with his Tesla cars, he builds like the whole system. Now that's his philosophy. I think all the other customers, all the other operators, no, they outsource. Like they launch with someone. They can launch with Arianespace. They can launch with Sput, with the Russians. What's the name? Well, Arianespace, the Russians. They can space. They can launch with Falcon, with SpaceX also. But they won't have launching systems of their own. They are not going to build their satellites by their own. They're going to go to the experts. They're not going to build the antennas by their own. I think that each business should concentrate in their core business, right? So if my business,
basically,
if my business is to operate satellites, so then I need to operate the satellites, and I need to go and buy, you know, each thing from someone else, and get the best from everybody. If I don't know, I'm trying to find an analogy to other things, but in essence, you know, no business should be self-sustainable. That is not good for the economy also, right? Business should rely on the expertise of others in order to bring the best of all worlds and integrate that in one solution.
Excellent. Now, finally,
yes.
you in a private conversation with me previously, you discussed mPOWER, and of course, when O3b started up earlier on, it didn't have the mPOWER technology. Could you give us a little bit of insight into how the mPOWER technology improves O3b?
Yes. So the mPOWER technology is a frog leap into the technology that we are, you know, implementing. This has been developed by us and by Boeing together. And let's mention a couple of differences. The first difference is the capacity. So the system capacity of the O3b constellation, I think, is around 150 gigabytes. The mPOWER constellation is going to be well above the terabytes of capacity. Another difference is that the O3b classic satellites, they could have 10 beams of a fixed size. And the mPOWER solution is going to be able to have each satellite up to 3,500 beams, and you will be able to define by yourself the size and shape of the footprint. You will be able to position beams anywhere in the world. You will be able to communicate between the beams. You will be able to communicate between sites that are in the same footprint of a beam. And that opens a very wide range of new applications like cellular backhaul and private networks for banks and etc. mPOWER is a software-defined satellite. It's going to be able to route communications between the beams. What else? There's a lot. I should have had a screen here with the advantages of mPOWER, but it's really the last word. It's the state of the art in satellite telecommunications.
I'm sure we're going to get another opportunity for you to bring back those. This will be number one for a sequel.
Yeah, the dynamic allocation is just another one that came into my mind.
So Daniel Shapiro from SES O3b, thank you for coming and joining me, John McKeown, for Tekedia Institute, and we'll be in discussions again, and I think we'll have more of these. It's been a great day. Thank you so much,
John.
Daniel.
It was a pleasure, and glad to do this.
Fantastic. Bye-bye now, Daniel.
Thank you. Bye-bye.
Thank you.